Now we're going to apply the algebra that we used in the preview activity in class to try to determine a linear combination of two integers that will give us the GCD of those two integers. For 8 and 12, it wasn't hard to guess what that linear combination had to be. We said -1 times 8 plus 1 times 12 was equal to 4, which is the GCD of 8 and 12. But when you have larger numbers, or numbers that are, not as apparently related to each other, it might be more difficult to determine the GCD as a linear combination of each of those two integers. Now, let's remind ourselves of the Euclidean algorithm that we used to determine the GCD of 426 and 246. Now, if you use the math of that preview activity, that algebra activity that we had in class, you would solve each of the remainders for their respective b and a, right? In other words, working from the end, we want to express 6 as a linear combination of 426 and 246. Remember, in the preview activity, we had the h at the very end. We had a, b, c, b, c, d, c, d, e, d, e, f, f, g, h, and then g and h. I might be off by my number of letters, but that's okay. The same pattern applies. We start with 6. We notice that it's 18 minus 12 times 1. We then use the next equation above it to solve for 6 in terms of 18 and 48. And to do that, we notice that 12 is 48 minus 18 times 2. So when we plug that in for 12, what we have in the next step is that 6 is equal to 18 minus 48 minus 18 times 2 times 1, which is 18 minus 48 plus 2 times 18. I didn't multiply the 2 times 18 because I want to keep track of my 18s and my 48s at this step, which means I have 3 times 18 plus -1 times 48. I'm writing it this way on purpose to indicate it's an integer linear combination of 18 and 48. Now the next step uses this equation. When I solve it for 18, I get 18 is 66 minus 48 times 1. So I'll plug that in for 18. Again, we're working our way backwards. We're trying to express 6 in terms of 426 and 246. We're working our way gradually to doing that. So we have 3 times, so we have 6 is equal to 3 times 18, which is now 66 minus 48 times 1, plus -1 times 48. And that comes out to 3 times 66 plus -4 times 48. And if you like, you can verify for yourself that this ends up being equal to 6. All right, next equation going up is, when we solve it for 48, we have 48 equals 180 minus 66 times 2. So I'm going to plug that in for the 48 here. And I'm going to get that 6 is equal to 3 times 66 plus -4 times the quantity 180 minus 66 times 2. So let's see. 3 times 66, because I have 3 66s. Let's show a little bit of additional work with this one. This one is slightly more complicated, this step. So we have -4 times -66 times 2. That's going to end up being +8 times 66. So I'll write that down, plus 8 times 66. We're thinking of the 66 and the 180 as variables, and we're combining like terms, which means we get 11 times 66 plus -4 times 180. We're going to need a little bit more room. To finish this off. And so what we have, well, which equation have we not used yet? We just used the 48 equation. Now we can solve the 66 equation, I'll call it. And so we have 66 equals 246 minus 180 times 1. And so we'll plug that in for the 66, which will give us that 6 is equal to 11 times the quantity 246 minus 180 times 1, plus -4 times 180. When we simplify this, we're going to get 11 times 246 minus 15 times 180. And then finally, we're going to use the very first equation from the Euclidean algorithm, solved for the remainder, as we've been doing with all the other equations. And we're going to get 180 equals 426 minus 246 times 1. And that will go in the place of 80. So we'll have that 6 equals 11 times 246 minus 15 times the quantity 426 minus 246 times 1. So we'll have 11 times 246 minus 15 times 426 plus 15 times 246. Again, thinking of the 426 and the 246 as variables, we quote-unquote combine the like terms, which means we'll get 26 times 246 plus -15 times 426 is going to equal 6. And this is exactly what we wanted. We've now expressed 6 as an integer linear combination of 246 and 426. So you might find this technique kind of tedious to do. The book offers a different way to do it. This is the way I personally prefer to do it. But you're completely welcome to read about the extended Euclidean algorithm and the 2-column format that the book offers to do that, to find the linear combination of A and B that will give you the GCD of A and B. I won't be covering it here. You're welcome to try and learn it on your own. But this is the technique we're going to use in this class. Now, in the final video for this section, I want you to practice finding the linear combination that produces the GCD of two integers. I'm going to slightly change the instructions. This part here, use the 2-column format. I'm just going to put that in parentheses. That part is optional. What you have to do, regardless of which valid method you use, is find the linear combination that produces the greatest common divisor of 153 and 732. And then as additional practice, find the linear combination that produces the GCD of 2,478 and 6,958. So go ahead, pause the video, try those. I won't be working them out in this video, but you're welcome to ask about them in class. So to summarize what we talked about in this section, we gave the definition of the greatest common divisor of two integers where they're not both 0, and that's the largest, which necessarily means it's positive, integer that divides both. We talked about the Euclidean algorithm to find the greatest common divisor, and I'm going to put again this part here in parentheses. The part I care about most in this third bullet point is we can find the special linear combination of two integers that produces their greatest common divisor. Whether you use the extended version of the Euclidean algorithm with two columns or the way that I demonstrated in the previous video, either way is fine with me. And then this important fact, which is in general a linear combination of two integers only gives a multiple of their greatest common divisor. That's why we have these special techniques to find the special linear combination that gives you exactly the greatest common divisor and not just a multiple of it. So now you should be ready to try the problems that are assigned on Canvas. So look for those, give those a try, and please bring your questions to class and to office hours. Thank you.